All right, so I've uploaded a new lecture for us on Canvas. So when you go into Canvas, there should be now lecture 6 as a folder. And inside of lecture 6, there is, it's really 2 lectures in one. The first part of it is going through thinking about how we should actually interpret regression models, how we can specify different models, and different robustness checks we basically need to run to make sure our specification is sound. The second thing we're going to do after that is something to help you guys with your projects, which is we're going to cover the topic of web scraping or collecting data from a bunch of different sources on the internet. Okay, so it's 2 lectures in one place. Hopefully we can get through both. I don't think we will, but that'll be the goal. Okay, so can you guys let me know when you've gone ahead and downloaded lecture 6 and you have it open in front of you?
It's downloaded.
Got 1 thumbs up.
Got it.
Wait, can't you guys do like a thumbs up thing? Yeah! Anna got it, Ami got it. There's some cool features to Zoom. And some
Where's that at? I couldn't find it.
I think if you like right click on a username or there's a more thing.
It's under reactions, I believe.
Something like
At
that.
the bottom, like where it says share
Oh,
screen.
okay. Found it. Cool, thanks.
Yeah, so that's one way to interact, you know, so it's just remains awkwardly silent for me. Okay, cool. That's lots of thumbs up. Does anyone have any questions from the stuff we did last week before we jump into everything that's new?
How are the tests looking like?
What tests?
The
Oh,
results. The ones that you have created so far. How's that?
Really good. You know, like what you would typically imagine for a take-home midterm.
Right.
Somehow everyone's just getting all the proofs right. I don't know what it is.
Right? Who would have thought?
Yeah. Okay. So I think that's everyone giving me a thumbs up. Oh, that's an even better way. So Annie just sent a thumbs up emoji. That works too in the chat. Okay. So we're going to get started with lecture 3. So I just started sharing my screen. Lecture 6, rather. There we go. Okay, so I know the class has kind of been thrown a little off now by the fact that we're not meeting in person every week, but I mean, truth is this isn't that bad, I guess. We still are going to hit everything that we had originally planned to do on the syllabus, right? So actually, let me pull up the syllabus for us really quick. You guys all see the syllabus now?
Yes.
Okay, so this was the original schedule I had put together for us. So basically we've covered, actually on the midterm, we were able to cover pretty much everything up to 0.5. So we actually hit everything we wanted to. I didn't dig into the qualitative variables and basically the diagnostics of regression as much as I would have liked to. So we're gonna actually do a little bit of that today. And then we're gonna pick back up with web scraping. After we do the web scraping stuff, then we're going to spend some time next week on they're called binary choice models. So it's basically, it allows us to leverage the regression framework we've been working with to, instead of like predict a test score or some continuous variable, we're going to be predicting the likelihood of something occurring. So like, what's the probability of someone with an education level of X having an income level of Y? Then we're going to spend some time dealing with spatial data. So historically, I've given a lecture on this, basically predicting different census tracts where a Starbucks location will exist. I might modify that. So imagine like you're working for the real estate team at Starbucks and you're trying to figure out where's the next location you should place a Starbucks store. You can develop a spatial model to try and predict where's the best place for you to do that. So we can do that, or I might modify it for us to focus on projecting where COVID is going to spread to. So we'll do a little bit of both. And then the last thing we're going to cover is sort of this idea of instrumental variables towards the very end. Then you're going to have your final exam and your term paper. So as far as time-wise for the rest of the class, right, we have today's lecture, and then we have 1, 2, 3, 4. When is the final exam in this class? Is it on the 18th? Does anyone know? Or is it on the 16th?
I think it's scheduled for the 11th.
Scheduled for the 11th? Okay. So historically, you guys would have presented your final exams on or your final projects on the 4th. Basically, the week before the final exam is when I have you guys present your projects throughout the rest of the semester. I think we can still do that. It would just be like you guys having a Zoom session like this, right? Where you would do a screen share and walk us through your presentation for 5 to 10 minutes. Okay, so we're still going to have the presentation on this last day of lecture. So really, we only have today and 3 more lectures left. Then it's your presentation, then it's your final exam, which is going to be a take-home exam again. Okay, sound good? All right. So today we're going to pick up really just spending the time to go through the interpretation of different regression models. Okay, we've done a lot of stuff where we're just talking about math, and we've done a lot of stuff where we're just working with simulations, which is awesome to derive the different properties of different estimators. But when you work with simulations, it basically, you become detached, right? It's just made up data. It's not real. Because it's not real, because it's not special, you don't really think about how to interpret it. You don't really think about what the units mean. You don't really think about those sort of questions, right? When you're dealing with actual data, you need to actually think about what's the best way for me to specify my model? What's the best way for me to code this variable? Should I just leave it in its level form? Should I standardize it? Should I take the natural logarithm of it? Should I square it, right? How do I figure out what's the best way to figure out my model? So hopefully today we're going to spend some time on that. And to do that, we're kind of just going to go through the basic schools data set that we looked at before, where we have the average test score at a school within a school district. And we have different information on like the proportion of students to teachers. So we can go back and test this idea of smaller classrooms lead to higher test scores. So we're going to spend some time basically varying the specifications, interpreting the models, thinking about how we should code up each of the variables, and then we'll also work on some diagnostic stuff. How many of you guys are actually pretty comfortable now with the idea of when you should use white standard errors? Okay, still not so clear. That's fine, because we've really only covered it theoretically, right? Today you're going
That's when you assume that the matrix has different variances, right, on the diagonal?
Essentially, you're saying the variance of the residuals is going to be different depending on the observation. Yeah, Roberto.
Yeah, what I've been able to gather so far is that you should use the robust model or robust estimator when you think that there might be, or when you see that there is heteroscedasticity on the error term, basically.
Yeah. So
And
let's see if I can. I've modified my setup a little bit from last week. Instead of a crappy stylus. I got the overpriced Apple Pencil. I think I changed my okay, so you guys should all be seeing my iPad now. Yeah,
Looks good.
cool. So basically, what we're talking about is this idea of the residuals, right? So we said whenever we include an intercept term, the expected value of our residuals is going to be 0, right? That's if we include an intercept term. What I've been talking about right now is basically this idea of what's the variance of epsilon. Or more precisely, really, what's the variance covariance matrix of epsilon? So if you were to take all of the residual terms and you were to look at the variance of them, rather in a variance covariance matrix, so it's like here's epsilon 1, epsilon 2, all the way up to epsilon n, epsilon 1, epsilon 2, all the way up to epsilon n. The terms on the diagonal are the variances, the terms off the diagonal are the covariances. That is, how does the error associated with the first observation covary with the error for the nth observation? That would be in this term here. We're going to always assume, for now, that those terms are actually 0. That is, the error associated with observation 1 is not related in any way to the error related to observation n. Okay. Now, under the Gauss-Markov assumptions, we assume that the variance of all of the residual terms is roughly the same. That is, we're assuming that the variance of epsilon 1 is sigma squared. The variance of epsilon 2 and epsilon 2 is also sigma squared, etc. It's all just sigma squared. They're all the same term. Okay, this is the idea of homoscedasticity. The variance or the spread of the residuals is the exact same for all the different observations. Right, so I'm not making errors in any systematic way. Make sense? When you introduce the idea of heteroscedasticity, I actually loosen this up a little bit. So then I say, well, it's not just that so I'm still going to assume the covariances are all 0, but with the white standard errors, it allows me to actually say that, well, really the error I get for epsilon 1, it might have one variance. The error I get for epsilon n might have a different variance. So it allows me to basically be more flexible in the variation of the error term. That's it. So it allows me to make errors in more systematic ways. Okay, this is going to become a little bit more clear right now when we go through an example. But that's sort of the general idea I want you to think about when you're working with basically different assumptions for the standard errors, right? So in all of this, we're still using the same Gauss-Markov assumptions, or you're still using the same sandwich estimator, right? So it's still the x prime x inverse x prime, and then this is the expectation part of epsilon, epsilon prime, conditional on x, x, x prime, x, inverse, right? That's our sandwich estimator. Okay. Basically, depending on the assumptions we impose on the variance covariance of the residual term, this thing, so this is our variance covariance matrix of the residuals. Right, so this is why we spent so much time walking through this last week. So it just depends on the assumption we impose here. That'll simplify out the way we calculate the standard errors of the estimator. Okay. Cool. So then let's go back and think about things now more at a high level, right? So this is sort of like, this is really like in the weeds of building a model, right? This isn't like the thing you would typically focus on when you're, rather it is, but it isn't the thing you focus on in your presentation, right? You estimate a model in order to actually gain some insight into something, right? So it's like, I want to understand the relationship between these two variables. That's the whole point of doing econometrics. It's not really like to just focus on the nitty-gritty stuff of standard errors or the asymptotics of it or do simulations all the time. If you want to do that, you can basically just be a statistician, right? That's what separates us a little bit. Okay, so today we're going to focus on sort of these 4 topics: interpretation of regression models, scaling the data in different ways and seeing how it impacts our interpretation of the model. Then we're going to do some regression diagnostics. And then we're going to jump to a different lecture, which is entirely on just collecting data from everywhere on the internet. Okay. So, like I said before, today we're going to focus in on that CA schools data set. We're going to look at the same relationship as before, which is we want to look at the relationship between the total scores that a student, the average total score that a student gets in a school, on their reading test and on their math test. So we're going to combine reading score and math score to come up with a total score for a student, average within a school. And we're going to control for this idea of a student to teacher ratio. That is, we're going to take the total enrolled students in that school, and we're going to divide it by the number of teachers in that school. Ideally, the smaller this number, that is, the more teachers there are relative to students, we'd expect a better outcome, right? Because then you can get more personalized education, supposedly, versus the alternative, which is if we have a very large number of students versus a small number of faculty, it may get a deterioration in the quality of education they receive. Okay, so one way of encapsulating that is basically through a regression. This is what we've talked about before, right? When we were just looking at the idea of correlations back then. So we can put that relationship into a regression where we're saying total scores is a function of student to teacher ratios. Okay, so beta 0 is our intercept, beta 1 is our slope, or it's basically the effect of student to teacher ratios on the total score. Right, and whatever is not captured by our student to teacher ratio, we're just going to toss inside of the residual term, epsilon I. Make sense? Okay. Now, we spent a lot of time on the math part. What does all this crap actually mean? Right? What is beta 0 here? Who can tell me? What is beta 0? Intuitively, don't tell me it's the intercept.
Like the smallest class size, I suppose, or like the right average. Yeah, like a student teacher ratio that you would have that everyone kind of has. The largest possible one you would have.
Beta 0 would be the smallest possible class you would have.
It will be the initial score, assuming that there were no students. So assuming that x1 was 0, or the ratio was 0, which will imply the beta 1 will be 0. That will be the initial score that you expect to have, I think.
Yeah, that's exactly it. Basically, beta 0 is the expected value of our dependent variable, in this case, total score, conditioning on all of our explanatory variables going to 0. Okay, so this is essentially the average after we control for everything else. Okay, so here we're saying, in this specification, beta 0 is the average test score, assuming a student-teacher ratio of 0. And if there is more than one x, right, then it would be assuming everything is at 0. Okay, so beta 0 isn't just there to make our residuals have a mean of 0. It's not just there to say we have an intercept. It actually has an interpretation, right? And the interpretation is it's the average of our dependent variable conditioning on all of our independent variables being 0. Make sense? Okay, what is beta? Yeah,
Can you please again explain?
sure.
Can you again?
So beta 0 is basically after we've taken out everything else, this is the average y.
Okay, thank you.
Okay. So how did you guys interpret beta 1 here?
It's the change in the test score when we increase the student to teacher ratio by 1 unit, holding all else constant.
Yeah, so it's basically, it's the effect that we're imposing on the student to teacher ratio. That is, we think that as the student to teacher ratio varies, beta 1 is how much we expect the test score to vary, the total score to vary. Okay. Another way of calling that is saying it's the partial effect. Okay. So again, each of these terms actually has a meaning. Okay. Now, rather than having us every single time we want to run a regression, actually like write the code for running a regression, I think we're okay now to use the built-in function in R, right? I think we're at a point now where after you've implemented the function yourself and actually understand the mechanics of what's going on under the hood, then I think it's okay for you to use the built-in functions in R. Okay. The reason is, again, there's a lot of assumptions being made in the base function in R when a regression is ran, specifically the Gauss-Markov assumptions, which hopefully you guys all know and love at this point, right? Okay, so we're going to use the data set from the AER package again. So if you don't have that package installed, I hope you do at this point, but if you don't, it's install.packages, and then in quotes, AER. Okay. If you want, you can update your package as well by running that. After you have the package installed, assuming you already do, you don't have to run that. You can just do library AER to load in the data or to load in the package. Okay. Again, this is that applied econometrics with R package. So first thing we're going to do is attach the data set from the package to our global environment. So we're going to do that by calling the data function and then the name of the data set CA schools. Okay, after we run that, we should see it appear here inside of our global environment, 420 observations of 14 variables, i.e. 420 rows, 14 columns. Okay, if we do question mark CA schools, we'll pull up the documentation for the package. And if we type in our console head CA schools, we'll be able to preview the data set. Okay, so again, we played with this data set when I asked you guys on one of your assignments to generate a bunch of maps, right? So you download the data set and you're able to plot out what proportion of the schools have higher reading score or which counties have higher reading scores versus which counties have lower math scores, or et cetera. But again, we have district number, the name of the school, the county the school is located in, and then the grades the school serves. Right, so KK is kindergarten, so that's like 1 grade before 1st grade for those that aren't in the United States. Total number of students, number of teachers, and the CalWORKs was the percent of individuals qualifying for CalWORKs, which is income assistance. Lunch, which is the percent of students qualifying for reduced price of lunch, the number of computers the school has, the expenditure per student, the income, the average income in that district. English, which is the percent of English learners, and then reading score and math score. Okay, so English is basically what proportion of people are actually learn or speak English at home. It's their native language. Okay. So the first thing we're going to do is combine the reading score and the math score into one new data or into one new column called total score. Okay. So again, when we're dealing with a data frame, so if you do class CA schools, you'll see that the object type is a data frame. Whenever we're working with a data frame, we can access all the information by the column names. So here I'm going into the object CA schools. I'm using the $sign to select the column read. And I'm adding to that vector another column inside of CA schools with the name math. So it's basically combining the average reading score with the average math score to come up with a total score, right? And this is going to be done element by element. That is, because these two vectors are the same length, we're going to take reading score 1 plus math score 1, reading score 2 plus math score 2, reading score 3 plus math score 3, etc. Okay, so if we run this bit of code, and if we preview the CA schools data set again, we're going to see we have this new column called total score, right? And so you're just aggregating those two columns together. Okay, this should all be pretty comfortable at this point. Next thing we're going to do is create another column called STR. So STR is again just going to be the number of students divided by the number of teachers. So student to teacher ratio. Okay. Now, to run this specification that I've defined up here, where I want to regress total score on the student to teacher ratio, it's actually pretty simple. All I have to do is run, or all I have to do is use the LM command, right? So again, LM stands for linear model. It's just doing ordinary least squares. Now, the way the LM function works is it takes in the name of the column you want to run the regression on, so your Y column. Our Y column is going to be this new variable we created, total score. And we're going to regress total score on our first X, or our first independent variable, which is going to be STR, the student to teacher ratio. Now, total score and STR do not exist inside of our global environment, right? They're not here. But what we can do is tell the LM function to look for these two columns inside of this data set, CA schools. Does anyone have any questions on that? This is an important thing to understand, because what if I have multiple data sets from different data frames?
I understand the function, but what we're doing here is like the two independent variables in my regression then are the total score and the star.
No, so total score is your Y variable. That's your dependent variable. STR is your one independent variable.
I see. And then if I had multiple independent variables, how would I go about that? Plus, okay.
Plus income.
I see.
Plus expenditure, etc.
Yeah, that makes sense.
We're going to start off with just the STR though.
Or you can use the $sign, right? Instead of, so without having to assign or without having to fill in the data command, like you can just grab it with the $sign.
That's exactly right. So one thing I can do is if I have multiple objects, assuming they all line up properly, I can literally just do something like this. Let's say I have another data set called CA schools 2, and then inside of there, there's a column called income. I could end up writing my specification like this. So then R is going to actually pull each of those individual vectors, even though they're coming from different locations, CA schools versus CA schools 2, as an example. This doesn't actually exist. And it'll run the regression using those two different data sets. Make sense?
Hesam, what form of data can you pass to this? Like, do they have to be data frame? Do they have to be matrix? Like, what is, like right now,
You can pass in an entire matrix, actually. So like, let's say I had an entire matrix of controls. I could literally toss in an entire matrix, and then each column would be treated as an independent variable.
Got it. So LM doesn't have any
Specific
restriction.
object type? No, it's very flexible.
No. Okay.
It can take in essentially a data frame, a matrix, or an individual vector. Okay, and by that I mean for the vector, it can be a string. So you can create things like dummy variables or categorical variables, which we're going to talk about in a little bit. It can take in a numeric vector, and it can also take in Boolean vectors, like trues and falses, which is the same thing as a dummy variable.
Got it. Thank you.
Yeah, but we're going to go back and keep it as it was, right? So you guys can keep following along with the lecture. Okay, the point of saying that is you guys should not be starting to think about, okay, I may want to get data from this place. I may want to get data from that place. How can I start cleaning it up and wrangling it in such a way that I can actually put it into a format where I can start asking and answering questions? Okay, so here we're going to run a regression where we're basically going to run this exact regression up here. Total score on beta 0 plus beta 1 times STR. Okay, notice I don't have an intercept term written in here. R is just going to automatically add in an intercept term for me. If for some reason I do not want an intercept, I can do 0 plus. That'll kill the intercept term. Okay, so again, by default, R is going to always add in an intercept term for you. If for some odd reason, and there are reasons sometimes, where you do not want an intercept term, you just do 0 plus, and that'll kill the intercept term.
Will that be the same as regressing through 0, like through the origin point?
You're forcing the intercept, or you're forcing the intersection into the y-axis at 0.
Got it.
That's exactly it. Okay, so you're forcing the line or the plane you're fitting. When all of your x's are 0, your y is also 0. Okay, and there's cases where you actually want to do that, but we'll deal with that later. Okay, so if we run this specification, that'll create a new object for us, right? It's not going to print anything out because we assigned LM to base model. Okay, this is a little bit different than other statistical packages where if you usually run a command, it'll just spit out the output, right? So like the Stata folks, if you just run a regression, you don't usually get an option to like save it or anything. You have to do like some weird like est-out crap to save it. Here you can just assign the actual entire regression model to an object called base model. Okay, so base model is itself a list. Okay, who here can describe what a list is again? Anyone? Anyone at all? What does a list look like? You guys are
I can give it a go. I think it will be a data frame with it has factors in it, which will be kind of different dimensions, I think.
It's like a collection of different data types.
Yeah, that's exactly it. It's a collection of different data types, right? More precisely, a list is essentially like a tree, right? So there's this key branch, or like this, there's this key trunk, right? That's like the base of the tree. Coming out of that trunk of the tree, the base of it, there's a bunch of branches. Okay. Each branch can contain an entirely different element. So for instance, the first element of the list can contain a matrix, right? Like 1, 2, 3, 4, 5, 6. It can contain in this case, it's a 2 by 3 matrix. The second element of the matrix can contain entirely something different. Cat. Just the word cat is a string. The third element of the list can contain nothing, could just be empty. And the fourth element of the list, well, that could contain an entirely different list. with its own stuff inside of it. It's very flexible. Okay. Okay, so the regression model is being stored as a list. And the reason why it's being stored as a list is because there's different things being returned. Okay, if we click on base model, okay, one way of accessing the elements of the list is by using brackets. You can use 2 brackets to select specific elements or specific nodes inside of the branch. Okay, so for instance, the first element of the branch contains, it looks like, coefficients, an intercept term, and then a coefficient on STR, beta 1. Okay, well, what's in base model 2? A bunch of crap. It's a vector. I don't know what it is. Okay, wouldn't it be nice if the elements of the list had names? Well, let's give this a go. If we type base underscore model, $, R will give me, or RStudio is going to print out for me a bunch of names. Okay. The first element of the list contains the coefficients. The second element of the list contains the residuals. The third element contains something called effects. The fourth element contains something called rank. Fifth is fitted values, and there's a bunch of other stuff in here. Okay, so we can access specific elements of the regression model just by using a $sign and then calling on different names. Make sense? Okay. Now, in the past, we've used the summary command to summarize data, right? It usually summarizes the data set for us by giving us the minimum, the first quartile, the median, the third quartile, and the maximum. And if there's any missing values, there's only the number of missing values. That's usually what we use summary for, right? To summarize like a vector of numbers. We can also run summary on a regression model. So if we do summary base model, that's actually going to print out this output for us. It's going to give us basically a nice regression table. Up top, it's going to tell us the formula that was ran. That is, our dependent variable is total score, our output or our independent variable is STR, and the data set is CA schools. We get a nice summary of the distribution of the residuals. So the minimum residual we have is -95, and the biggest residual we have is 97. We get a table here that has the estimated coefficients, the estimated standard errors under the Gauss-Markov assumptions, the t-statistics, which is essentially, now that you know from your midterm, the estimated coefficients divided by the standard errors, that gives you a t-statistic. What is this t-statistic testing? What's the null hypothesis in this t-statistic?
Beta equals 0.
What was that?
Beta equals to 0.
That's exactly it. So the default test that is automatically being ran for you here is that this coefficient is equal to 0. That's the null hypothesis. Okay, so the null hypothesis is right? That's our null hypothesis. Every beta I is equal to 0, and that's being ran individually for all I. Okay. The alternative is a two-sided alternative, which is simply beta I is not equal to 0. Okay, that's what this t-statistic is giving you, right? So it's either positive or negative to generate the t-statistic, but the significance level of is this actually statistically different from 0? It's being tested against a two-sided alternative. So it doesn't matter if it's positive or negative, you'll still get the same p-values of less than, at this case, the 1% level. Okay. You also get a couple more things. You get the residual standard error. You get the multiple R squared. What was R squared again? What was that whole thing? Remember, we actually spent a day, I think it was the last lecture we had face-to-face. It was a special lecture.
goodness of fit, which is the ratio of, if I'm not mistaken, the explain over the total of the residual. So SSE over SST.
Yeah, that's basically it. So the whole concept of R squared was basically comparing the explained error in the model. So basically, how much variation are we capturing of the dependent variable? Okay, or in other words, go away. There, okay. R squared was essentially the explained sum of squares, or what do we call it? SSE? No. What was the exact notation I used before? I don't want to throw anyone off when they're going back and reviewing the lectures.
No, you're okay. SSC over SST.
Okay,
You're fine. Yeah, yeah.
cool. I want to make sure I'm not throwing anyone off. Okay, so SSE was essentially the explained sum of squared errors. Okay, and what was that formula?
SSC over SST, the total
Yeah,
errors.
so what was SST? SST was the easy one. It was summing across all I observations. We were looking at simply the difference between
The expected value, which is the average of Y minus the observation of Y. That's SST, right?
yeah. So basically, we were looking at this. We were looking at. Wait, are you guys seeing my iPad screen? Or no?
Now we are.
Damn. I'm writing to myself. Do you see it now? Yeah, I'm totally lost. You guys see my iPad?
Yes.
Cool. I'll take your word for it. Okay. So the explains or the total sum of squares was basically how much variation is just predicted by the average, right? This is the error from the average. Okay. The explained sum of squared errors was yi minus yi hat. Basically, this was the result of our fitted model. Make sense?
I think it's residual. It should be y hat minus y bar, I think.
Let's see.
Yeah, I think Kendra is right. It's y hat I minus y bar square.
So no, what am I doing? Slow day. There we go. Okay. So how did we interpret R squared?
How much variation in Y can be explained by the model?
Right. So R squared we said was going to be bounded between
-1 and 1.
0 and 1. Essentially, if a model has no explanatory power, that is, it's not better than just including a simple intercept term, then the R squared would be 0. If a model provides more explanatory power than the average, then we would have that the model's R squared would be approaching 1. Sorry, I'm just going back and checking my notes to make sure I'm not messing up royally. No, that's all correct. Cool.
Sir, I have a question.
Yeah.
Is the 0 to 1 is like the percentage, right? Like the percentage of the variation, right?
Yeah, that's exactly it. So there was a detailed proof we did back in lecture 3. Okay, so in lecture 3, let me jump to this. Can you guys see my actual desktop screen now? Yeah, okay. So this was from lecture 3, right? So we had the total sum of squares was just yi minus y bar. The explained sum of squares was y hat minus y bar. And the residual sum of squares was y hat, or the residual sum of squares was y hat minus yi. Then we did this proof, which showed us basically we could derive the r squared as being the ratio of the explained to total error. Okay, so basically, as we explain more of the error relative to the average, our model is getting better and better, right? And again, it's on a relative basis where it's relative to just including a simple intercept term. So that's kind of our benchmark. Okay, so r squared is bounded between 0 and 1. Adjusted r squared is not. Adjusted r squared has the ability to go negative. And the reason why is adjusted r squared basically adds in an additional punishment for the number of variables you control for. So as you control for more variables, you should be getting a better model. If you're not getting a better model, the r squared can go negative, right? So if you ever find yourself with a negative r squared, give yourself a nice pat on the back. You've done worse than just including an intercept term. Okay. Now, down here, there's also something called an F statistic. Okay. We haven't really talked much about an F test, but hopefully you guys reviewed it in your book, which I asked you to do at the beginning of the semester. An F statistic is essentially doing a joint hypothesis test. It's testing if the entire model in this case is statistically significant from 0. That is, the null hypothesis in the F test is going to be beta I equal, it's going to be, in this case, beta 0 equals beta 1 equals 0. Basically, we're testing jointly beta 0 and beta 1 are both equal to 0 at the same time. Okay, versus the alternative, not the case. There is something in the model, any one of these, beta 1 or beta 0 is different from 0. Make sense?
Can we say at least one beta not equal than 0?
Correct. So it's basically, is this model informative at all? Okay, so that's kind of the high level statistics that are being reported from the base function in R. Okay, again, the standard errors that are being reported are the standard errors under the Gauss-Markov assumptions. That is homoscedasticity of the variance covariance matrix of the residuals. Okay, now the things that are really of interest to the econometrician or towards anyone interested in asking any real question is basically the coefficients and the standard errors. Those are the key things that really matter, right? Everything else is there to help you diagnose, is this a good model or not? So our point estimates here, our beta 0 is 1,397.8659. Our coefficient on STR, the student to teacher ratio, is minus 4.55. Okay, so what's my beta 0?
Negative, oh no, beta 0 is 1397.86.
And beta 1 hat?
Negative 4.5596.
Perfect. So really, that becomes our new model, right? Those are our estimated coefficients. We can literally just plug them straight in.
So going back to this, sorry, I know we talked about a lot about the R square, but going back to this, like the adjusted R square, but when we explain it, we say it's basically punishing you for the additional variable that you control, but I'm not controlling any variable. Like, how does it know which one I want to control?
Oh no, it's basically accounting for the number of variables that you control for. So it's
Oh, so beta 1 in this case, right? Beta 0, it's all done by the R, but beta
so
1, it's the one I'm controlling.
basically, it's basically saying, so this is the formula. Can you guys see my screen share? All right, so it's a quick Google search. This is how the R squared is being adjusted. Essentially, it's taking the R squared and it's punishing it by this additional parameter of n minus 1 over n minus k minus 1. So n is the total number of observations you have. So as n grows, that is, as n tends to infinity, R squared and adjusted R squared are going to be exactly the same. Okay? So as n grows to infinity, R squared and adjusted R squared are going to be exactly the same. In smaller data sets, there's usually going to be some difference between the two. It's usually pretty small. But n here is the total number of observations. K is the number of predictors in your model. In our case here, K is 1. We only have one predictor. We're already subtracting out a 1, which is the constant term. So really, we're controlling for 2 degrees of freedom. The constant term and beta 1. Make sense?
Yes, and then going back on the results of the regression, is the multiple R squared the same thing as R squared?
Yes.
Is it? Okay.
Exactly the same thing. So R squared and multiple R squared are the same thing. The differences between the R squared and the adjusted R squared is basically just a sample size correction and a degrees of freedom adjustment. Okay, so really the thing you should actually be focusing on is adjusted R squared, because that's basically a way of comparing models where you can have different numbers of variables in them. So like if I have one model that has 3 independent variables and it has an adjusted R squared of 10%. If I have another model that has 20 variables, also has an adjusted R squared of 10%, which one should I go for? Okay, let me write it out. How about that?
Well, it depends if you're going for simplicity or you're going for more explain, but you're not gaining anything by adding those additional explain variables. Is that what you're trying to getting at?
Exactly
Okay.
it.
Okay.
Right, so again, let me write it out as an actual example. So if I have model 1, right, and that has adjusted R squared of 10%, okay, and it has 3 xi's. Model 2 has an adjusted R squared of 10%, but it has 20 xi's. Obviously, I should go for model 1, right? It's a more parsimonious model. It only has 3 variables inside of it. And it's still giving me the same amount of explained or adjusted R squared. Now, typically what will happen actually is the R squared of the second model here that has 20 variables, this might have an R squared of 25%. And this model might have an R squared of 15%. I'm exaggerating, it's never going to be that big of a correction, okay? It could be that after I adjust for the fact that I'm adding on and burning these extra degrees of freedom, that I'm better off just using that smaller, more parsimonious model. Okay? This is why you can't really compare 2 models that have different numbers of variables on just R squared. You want to adjust them for the number of degrees of freedom you burned or for the number of variables you're using, then you can compare them more fairly.
Got it. This was really helpful. Thank you.
Good. Okay, back here. Getting a little smoother with the transitions. Okay, so again, this was the model we estimated. We're saying total score is equal to 1,397.8659 minus 4.5596 times STR. Okay. So here I've written, so throughout this lecture, I've written basically a bunch of questions for us to try and stimulate some sort of discussion, even though we're not face-to-face. Okay. What does the intercept mean here? So when I say the intercept is 1,397.8659, what does that mean?
That means the average score of the class is is 1397.
Sure. So basically we're saying if the student to teacher ratio is 0,
Yes, yeah, exactly.
what's the average score?
That's the one.
Okay. It's 1,397.
Yes.
Okay. Now, our estimated partial effect, that is, as the student to teacher ratio changes, we expect the total score to also change. Now, what's the units here that we're imposing? The units for student to teacher ratio is just students to teachers, right? So if we go from 10 students per teacher to 11 students per teacher, we're basically saying the classroom size grew. If we go from 10 students per teacher to 9 students per teacher, we're saying the classroom size shrank. Okay. Now, the way we can actually think about these models is in terms of, rather, if we want to see the effect of the student-teacher ratio on total score, it essentially is
Easy.
so the model we estimated, right, is total score equals 1397 minus 4.55 times STR plus epsilon hat, right? And those are beta hats. Okay. If we want to figure out the impact of a change in the student-teacher ratio on total score, basically what we need to do is take the derivative of total score with respect to the student-to-teacher ratio. Okay. What is that derivative? What's the derivative of 1397 with respect to STR? 0, it goes away. How about this second term?
4 point or negative 4.
Negative 1.
4.5.
Okay, and how about the residual?
Is 0.
0. Okay,
Yes.
so basically we're saying the change in the total score as the student to teacher ratio changes is minus 4.55. Okay, another way of writing this is actually by just cross multiplying, by taking the change in the student teacher ratio and just moving it over to the right hand side. So then you have the change in the total score is equal to minus 4.55 times the change in the student to teacher ratio. Okay, so as the student to teacher ratio increases by 1 unit, so if student teacher ratio goes up by +1, then the total score predicted for that school is going to go down by minus 4.55. Alternatively, if the student to teacher ratio goes down by -1, so it goes down, the change is -1, then the impact on the student on the predicted test score is going to be plus 4.55. Okay, and that's going to stay constant regardless of where the average test score is. As we keep adding one additional student to teacher ratio, right, or as it keeps increasing by 1 unit, the test score is going to keep dropping continuously by 4.55. So in other words, if we were to plot out this relationship, we have the student to teacher ratio running along the x-axis. Along our y-axis, we have the total score, right? Or the predicted total score. We'll put a little hat over it. Okay. We said the intercept term was $1,397, right?
137, 1347, something like that.
1397.
Yeah, exactly.
Okay, 1397. 1397 was the intercept. That is, when the student to teacher ratio is equal to 0, the predicted test score per school is going to be 1,397. That's 1 point. Okay. Another point is when we have a student-to-teacher ratio of 1. If we have a student-to-teacher ratio of 1, what's going to be the predicted new test score?
You just add.
Sorry?
Are you saying if the student-teacher ratio increased by 1?
Yeah, so if we go from 0 to 1.
Yeah,
What's going to be the new
goes
total
to
score?
1393 because we have to minus 4.
Yeah, so it's going to be 13, roughly, it's going to be 1392.5, right?
Exactly.
Or 45, right? The next point, if we student-teacher ratio goes from 1 to 2, it's going to be minus another 4.55.
Yes.
Okay. Here's an issue that can emerge with our model. Is it possible for a test score to be less than 0? I mean, some of you, right? Maybe.
No, because the intercept should be the b naught should be 0. So how do we go beyond 0? The score cannot be negative.
It can. What if I have a student-to-teacher ratio of 1,000? There's 1,000 students per teacher. It's unlikely, but what if I have that, right? I get this weird anomalous school that for some reason just doesn't fit my model, and I have 1,000 students per teacher. It's an online school.
But intuitively, the worst that you can do in the test will be to get a 0.
Right. Our model doesn't know that. It's just a mathematical model. Okay? It assumes the entire domain of the student-to-teacher ratios is possible. It's assuming that the student-to-teacher ratio actually spans minus infinity to plus infinity. A regression line doesn't know this shit. It's just a mathematical line. Okay? So technically speaking, although I've drawn the student-teacher ratio to stop at 0, that's not my regression line. Technically speaking, my regression line covers the entire domain. Okay? Make sense? Now, this doesn't necessarily pose serious problems for us. Okay? There are ways to correct models for censored data. Okay? If you're interested in this sort of thing, look up censored regression models. You're probably going to see that more, and actually you will see that in your next econometrics class. Okay. So there's something called censored regression models that are specifically designed to deal with data that's censored. It doesn't go beyond a certain range. Okay. Most of the time, you can ignore it. It's not going to make that big of an impact, but there are corrections you can do. Okay. Does this help a little bit with thinking about how to interpret these models? Good? Okay. Cool.
Sir.
Yes.
There is another schools of thought which says that the more STR, the more understanding by the students, so the more the total score. And the argument behind this is that maybe we assume that more students can share ideas than few students. So the more the students, the best the total score. How do you take that?
Yeah, so that's also an option, right? So the alternative is having more students in a classroom.
Yes.
Can potentially lead to more ideas spreading around the classroom, or if a student is shy, another student may ask a question on their behalf.
They increase more understanding among students.
Yeah, which could lead to more understanding, which could lead to a higher test score or a better performance or a better outcome. The truth is, though, the data doesn't seem to support that as of now.
Okay.
Okay, so I'm trying to jump back into my desktop, but Zoom is totally frozen. Cool. Can you guys see me?
Yes.
Can you hear me?
Yeah, we can see and hear you.
Okay. Are you guys seeing anything, any screen being shared at the moment or no?
No.
No.
Okay. Here's what we're going to do. Since Zoom is totally frozen on my part and I can't share any screens, we'll have our break now. So it's 2:14 right now. So we'll pick back up in 15-ish minutes. Okay. Keep the Canvas page open. I'm going to have to end this meeting and start another meeting because I have to quit out of Zoom. Okay.
We're gonna use the same ID.
Maybe I can just, yeah, tell you what, I'll try this. I'll leave the meeting and then I'll try and rejoin it. So it'll stay open for you guys.
Okay.
So I'm going to make you the host for now.
Okay.
And then I'm going to leave and then I'll join you guys in 15 minutes. Okay.
Mhm.
So I'll pick back up at 2:30.